guys and welcome. In today's video, I'd like us to focus on complex numbers. Okay, so let Z be an element of the complex number. And say that Z is defined by A plus BI, where basically now, in a sense, we have the A, B are elements of real numbers. Okay, then this is the standard form. Okay, so Z equals to A plus BI is the standard form of the complex numbers. So for those of you who maybe do not have an idea, I is basically an imaginary number. I is the imaginary number. Then, in a sense, that you should keep in mind that I equals to square root of minus 1. Okay, so if I is equals to square root of minus 1, it implies that I square equals minus 1. Okay, so keep this in mind. It's going to be really important as you proceed and do examples of complex numbers. So now, if we consider Z bar, Z bar is basically what we call the conjugate of Z. Okay, so this is the conjugate. So the conjugate of Z, in a sense, if Z equals to A plus BI, then Z bar will be A minus BI. So you basically change the sign of B. So B here is positive. On the conjugate, it will be negative. Okay, so that is where you change the sign. For an example, say maybe you have Z equals to 1 plus 3i, then it means that the conjugate of that one will be 1 minus 3i. So that is the basic idea of dealing with the conjugate. Okay, sometimes they can put it like this, say maybe Z equals to I don't know, 7i minus 1. Then it implies that the conjugate of that one will be minus 1 minus 7i. Remember I said that you change the sign of b. So b here is positive 7. Then for the conjugate it will be negative 7. Do not change the sign there because that will be incorrect. It won't be the conjugate of z. Okay, so that is the basic idea. So let's proceed and look at some few examples that they will need us to express in terms of the standard form. So we can say that we should express the following in the form Z equals to A plus BI, right? Then let's look at the first one. Say you are given Z equals to, I don't know, 12 plus 7i. So this basically means that Z is basically the conjugate of this complex number 12 minus 7i. Okay, so in a sense, then Z is just going to be the conjugate of 12 plus 7i. We change the sign of B, then it was positive. Now on the conjugate, it has to be 12 minus 7i. Okay, so that is Z like that. Okay, so let's look at another one. Say maybe you are given Z equals to 1 all over 1 plus I. So how do you write this in the form A plus BI? Okay, how you do it, you just multiply by the conjugate of Z. So in a sense, you'll have that Z equals to 1 all over 1 plus I. Okay, then times the conjugate of Z is 1 minus I. Then you divide by that, 1 minus I. So this is basically the idea that you're just multiplying this by 1. Okay, then the reason we do that is to get rid of the complex number there, I, to get rid of I at the bottom. So we'll basically get that Z is therefore just going to be 1 times 1 minus I, that will be 1 minus I. Then divided by, at the denominator there now, we're just going to get that we have 1 plus I, then times 1 minus I, isn't it? Yes. Then, I don't know, say Z will therefore be 1 minus I divided by 1 times 1 is 1, 1 times I is minus I, then I times 1 is positive I, then I times minus I, that will be minus I squared. Okay, so remember that I said I square is minus 1 like that. Okay, so keep that in mind. It will be helpful where we see I square plug minus 1. So here we'll plug minus 1. Then basically now we'll therefore have that Z equals to 1 minus I over 1. Then minus I plus I is 0. Then minus of, we replace I square with minus 1. So we'll have minus of minus 1. So basically Z is just 1 minus I divided by 1, say plus 1. So at the denominator, they will will end up having 2. So we have 1 minus I over 2. Okay, so we need it to be expressed in the form a plus bi. So we can divide each term there at the numerator by 2, such that we end up having half minus 1 over 2i. Okay, so this is now your value of a, and that one is your value of b. So it is expressed in the form z equals to a plus bi. So that is how you do it. Okay, yeah, that is the basic idea. So say maybe let's look at another example. Say maybe you are given something like I don't know, z equals 3 plus I divided by 1 1 minus 2. We can put it like that. Then how do we express this one? Similarly, again, we just multiply by the conjugate of what is at the denominator there. So the conjugate of 1 minus 2i is just gonna, we change this sign to positive, the sign of b, okay? Then we'll have 3 plus I divided by 1 minus 2i. Then we multiply by 1 plus 2i over 1 plus 2i. Okay, so then now we'll basically get that z, it's nothing but 3 plus I. Then that will be multiplied with 1 plus 2i. Then divide that thing by 1 minus 2i times I don't know, 1 plus 2i. So basically, you get that z in a sense now is gonna be 3 times 1, that will be 3. Then 3 times 2i, that will be plus 6i. Then say I don't know, I times 1, then that will be I. Then I times 2i, that will be plus 2i squared. Okay. Then remember, always you have to replace I squared with minus 1. We'll do that on the next step. For now, then we'll go to the denominator. This is gonna be a the denominator. Then it's gonna be 1 times 1, that is 1. Then 1 times I don't know, 2i, then that will be 2i. Then minus 2i times 1, that is minus 2i. Minus 2i times 2i, that will be minus 4i squared. Okay, so we have minus 4i squared. So then z is basically going to be I don't know, say 3. Remember, we have to change that I squared. So if we plug I squares minus 1, here we'll have minus 2. Then 3 minus 2, that will be 1. Then 6i plus I, that will be plus 7i. Then divided by, say now here, 2i minus 2i, that will be 0. Then we're basically left with 1 minus 4. Then replace I square with minus 1. Then we'll have minus 4 times minus 1, that will be positive 4. Then 4 plus 1, that will be 5. So the denominator will end up with something like that. So then now if we write it in standard form, we basically going to have 1 over 5, then plus 7 over 5. Okay, so this is then now expressed in the standard form. Okay, so you can do the same with multiplication of two, what you call complex numbers and so forth. So this is just the arithmetic of complex numbers. Okay, so yeah. So now let's move on to another concept. Maybe they say they give you, I don't know, and maybe a quadratic equation. It can be anything. Okay, but then since now we are still trying to build up, say maybe they gave you an equation and they say that you should find solution of the equation. Say that equation maybe, I don't know, it's x squared plus 2x plus 5 equals to 0. Okay, yeah, if they gave you something like that, then what is it gonna be? Okay, before I do this one, let me show you one last example on the arithmetic. Say z equals to square root of minus 60, and you want to write this in the standard form, z equals to a plus bi. Okay, so how do we do that? How you do that, basically you're going to just say that z here is the same as square root of minus 1 times 16. So you can rewrite minus 16 as minus 1 times 16 like that. Then basically z will be root of minus 1 times root of 16. So then this is going to be what? Root of minus 1, remember what is root of minus 1? Root of minus 1 is I. Then root of 16 is 4, so basically this will become 4i. Okay, so this idea, we're going to apply it when we are solving, I don't know, say this quadratic equation right there. So then let's come back to this one. We have x squared plus 2x plus 5. Then how do we solve this one now? We're just going to say that x should be equals to I don't know, say minus b plus minus root of b square minus 4ac divided by 2a. So basically now here you're just trying to use what you call the quadratic formula that you know to solve the things. Okay. So what is b? B is 2 and a is 1 and c is 5. So you're just gonna plug in the things in there and say you will end up having x equals to minus 2 plus minus square root of I don't know, say 2 square minus 4 times a is 1 and c is 5. Okay, then divide that by 2 times a is 1. So you're just going to have x equals to minus 2 plus minus square root of, now you will have 2 squared there, it's 4. Then minus 4 times 1 is 4. Then minus that minus 4 times 5. Then that will just basically be minus 20. Okay, so yeah, then divided by 2. 2 times 1 is just 2. So x is equals to, I don't know, here we'll have minus 2 plus minus square root of 4 minus 20, that is minus 16. Yeah, and the discriminant here it's minus 16. That is just by coincidence. Okay, but then it doesn't necessarily mean that always in here you will find minus 16. Okay, because remember earlier on before I did this problem I showed you guys how to rewrite this in standard form. Okay, then yeah, you can do for basically anything. Even if you had z equals minus 25, you can still do the same thing. Say z will be root of 1 minus 1 times root of 25. Then you will get 5i. Okay, so that is the basic idea. I don't want you guys to get confused with the idea that always under the discriminant you have to find minus 16. No, that will not always be the case. Okay, so it's just a coincidence for this problem. Then here say divided by 2. If we come back to the problem that we're trying to solve, then basically now we can say that x is just going to be I don't know, minus 2 plus minus, we know we can rewrite square root of minus 16 as square root of minus 1 times square root of 16, then divided by 2. So basically x is just going to be minus 2 plus minus, what is root of minus 1? That is I, and root of 16 is 4. So we're basically going to have 4i divided by 2. So now it's high time you just I don't know, divide each term there by 2. So x will just be equals to minus 1 plus minus 2i. Then we have our solutions as x equals to minus 1 plus 2i, or x equals to minus 1, x equals to minus 1 minus 2i. Okay, so that is how you will solve the equations like that. Okay, so get into the idea of what you have to do. Basically, if you are given a quadratic equation like this one, they can give you anything. So far, do not think about it too much. I don't think it will build up as of yet to where you have to find the roots, okay, of the complex numbers. So we can stick to this idea for now. Okay, then let's move on and build up a bit. Okay, so we know in standard form z equals to a plus bi, right? So if z equals to a plus bi, can we try and plot this on the imaginary complex plane? So on the imaginary complex plane, we can see that since here z equals to a plus bi, we basically have the real part of z equals to a, and the imaginary part of z equals to b. Okay, so the imaginary part of z is b. Okay, so this is the real part and that is the imaginary part. So keep that in mind. Okay, so yeah, I realize I didn't say anything about that. So if you have z equals to 3 plus 2i, then it implies that the real part of z is 3 and the imaginary part of z is 2. Okay, so sometimes they can give you something that you first need to solve, like the first examples that we did there. Okay, you have to simplify it. Then they will maybe be looking for the real part of z or the real part of the imaginary part of z. Say maybe they gave you something like 3 plus 8i divided by 1 minus 2i. Then they say you should find the real part of z and the imaginary part of z. You cannot like right away tell what is the imaginary part of z and the real part of z from this one. You have to first simplify this quotient the way that I showed you on the previous examples. Okay. Then after it is in the standard form a plus bi, then you take the one that represents a as your real part of z, the one that represents b as your imaginary part of z. Okay. So that is the key size idea. So now, if we have z in the standard form like this, can we go back to the idea that I wanted to talk about now? Maybe let me just go a bit down. say z equals to a plus bi, like that. Okay, so if you have something like that, can we put it on the imaginary complex plane? Say you have your Cartesian plane like that, where now the x-axis will present the real axis, and the y-axis now will be our imaginary axis. Okay, so if we have something like that, remember now, we can say a, since it's the real part of z, is somewhere there, and b, since it's the imaginary part of z, is somewhere there. Then this complex number makes a point, say somewhere there, then we can construct a straight line from the origin to that point. Okay, then notice that if we dot like this go into the real axis, then we can construct a right angle triangle. In a sense, now we'll have an angle between the real axis and our complex number z. So this line is z. Okay, so we have an angle right there. So that angle, we can call it theta. We can call that angle theta right there. So notice that about our angle theta, theta is what we call the argument of z. So theta is the argument of z. Then how is it measured? It's measured I don't know, say anti-clockwise. Then now say this hypotenuse, we label it r. Okay. Um Then let's see what we can do with this right angle triangle that is formed right there. From this right angle triangle, we can see that sine theta will be opposite. So this side, it's the length b, and the adjacent side is the length a. Okay, so that implies now sine theta is basically gonna be b over r, opposite over hypotenuse. Our hypotenuse is r, then basically b will therefore be equals to r sine theta. Okay, then similarly we can do for cos theta. Say cos theta, we know that it's adjacent side over the hypotenuse, then it's basically going to be a over r. Then in a sense now it implies that a is basically going to be equals to I don't know, say r cos of theta. Then now substitute this value of a, r cos theta, and value of b, r sin theta, into the standard form of z. So if you substitute a and b there, what are we going to get? We're going to get what we call the polar form. So we're going to get the equation of the polar form. Say now z will be equals to r cos theta. This is when we substitute for a, then plus I r sine of theta, like that. Okay. Then now notice that you have r as common between these two terms, then we can factor it out. Then in a sense, z is going to be I don't know, say r into cos theta plus I sine theta. Okay, so that is the case. Then this gives us the polar form. So this one is what we call our polar form. Okay, so now let's see if ever we can use this equation to transform or to convert from the standard form. Say you are given z in standard form, and then now they want you to write it in polar form. Okay, let's look at an example where we can do that. For this particular example, we'll focus where the argument, the argument of z, the big argument of z, it's it's an element between 0 and 2 pi. Okay, we'll focus when it's between 0 and 2 pi. They can also specify that it will be between minus pi and pi, but then we'll start with 0 and 2 pi, then we can go to minus pi and pi thereafter. Okay, so let's look at when the big argument of z is between 0 and 2 pi. So now what we're going to have is that this big argument of z, it's called what? The principal argument. Before we do an example, let's give it a name. It's the principal argument. And the principal argument, it's what? It's unique. This one is unique. That implies that the angle that we're gonna find called the principal argument of z, that is the unique angle of that complex number. Otherwise, the small argument of z, we use our small letter a. The small argument of z will be equals to I don't know, say theta plus 2 pi n, where n is an element of integers. It's an element of integers like that. Okay, so this theta in a sense now will be our big argument of z. So let's say maybe for an example, you are given that z equals to I don't know, say 1 plus root 3i. Okay, this is in standard form, and they want you to write this z now in polar form. Okay, so if we want to write it in polar form, we first look for our modulus r, and we know that it's given by root of a square plus b square. So now this is basically going to be root of our a, it's 1. Okay, so we have 1 squared plus root of 3 squared. Then basically now we see that r will basically be equals to what? R will be I don't know, 1 plus root of 3 square is 3. So 1 plus 3 is root of, then we're going to have root of 4, and root of 4 is 2. So we get r is 2. Then now we need to find the angle theta. Okay, in order for us to get the angle theta correct, let's go and plot this on the plane. So we're gonna have our imaginary real axis plane. So this is the real axis, and that one is the imaginary axis. So we see that it's positive 1 and root 3. So where they meet, say maybe it's somewhere there, then we construct a straight line. This describes z. Okay, so this slant line, the hypotenuse, it's z. So now what we can have there is that we can construct our right angle triangle. Then since theta is measured from the positive real axis, then we see that it's gonna be an angle right there. Okay, so if it is in the first quadrant, then we know that we can find theta basically to be just arctan of b over a. So this is basically arctan of, I don't know, say what is b? B is root 3, so root 3 over 1. So we're basically looking for arctan of root 3. Arctan of root 3 is what? Pi over 3. Okay, so theta is pi over 3. So this is the angle that we're looking for, and it's basically in the first quadrant. So you take it as your big argument of z. So this is the big argument of z. Okay, so this is the angle that we're going to substitute into the equation of z in polar form. Okay, otherwise the small argument of z, then we know that is going to be what? Theta plus 2 pi n. Okay, where n is an element of integers. Then that theta there, it's pi over 3 plus 2 pi n. Okay, so in a sense now we see that the small argument of z, it's all possible set of our angles that we can find. So if you vary n, choose n as y, you will have pi over 3 plus 2 pi. So that is the angle that you can get if you take a full revolution from this angle. Say you start from there, you take a full revolution and come back where you started. So this is full revolution 2 pi. Okay, that is another angle that you can get. Okay, of z. But then now this one, it's unique of pi over 3. That is why we call it a big argument of z. Then let's go and write our z in polar form. It's gonna be r cos of theta plus I sine of theta. But then what is r? We know that we got r as 2. Then we have 2 into cos theta plus I. We also have to substitute theta there. We got theta as pi over 3. It's right there. So we have cos of pi over 3 plus I sine of pi over 3. Okay, that is the angle that we get when we are focusing on the interval 0 to 2 pi. Okay, then let's look at another example. Say maybe you are given z for number 2. You are given z equals to I don't know, we can put anything, say 4 root 3. Let's use minus to change the quadrant. Minus 4 minus 4i. Okay, so now if we are having this, where is it? Sketch the thing to check the quadrant. So we have the imaginary and real axis. Which quadrant are we at? A, it's positive, so it's somewhere there. Say 4 root 3, it's somewhere there. Okay, but then b it's negative. They on the imaginary axis, say maybe I don't know, 4 minus 4 is somewhere there. Then where they meet, you make a point, then you construct a straight line from the origin to that point. Okay, then check now your right angle triangle is something like that. And then your angle theta, since you measure it from the positive real axis anti-clockwise, it's gonna be this whole angle there. This whole angle is your theta, that one. Okay, so that is theta. So basically what you're gonna find from using the right angle triangle is that angle there. And that one you will call it your reference angle. This is gonna be your reference angle now. Okay, so you're gonna have alpha is your reference angle. So we can quickly start by calculating our modulus r. So if you calculate our modulus r, we know that it's gonna be 4 root 3 square, then say plus minus 4 square. Okay, so r will basically be equals to 4 square is 16. Then I don't know, multiply that by root of 3 squared, it's gonna be 3. So we need just 16 times 3. So that will be under the square root, we'll have what? We'll have 40, 42, then plus 16, isn't it? Yeah, 16, 6, so it's 48 here. Yeah, not 42, 48. Here it's 48. Then add these two, then you will get I don't know, 48 plus 16, say, then what is it gonna be? 58 plus 2, 60 plus 4. So r will be root of 54. So you can just confirm if this number is correct there. Okay, then we get r is root of 54. So if r is root of 54, let me just quickly confirm that. We have 4 root 3 squared plus 16 root of 54. 4 root 3 squared 48, and 48 plus 16. Oh, it's not 54, it's 64 there. Here it's 64. If you confirm that, you're gonna get 64. Okay, then I don't know, root of 64, then we know it's just gonna be r equals 8. So we get r as 8. Okay, so if you take the root of 64, yes, that is indeed 8. So we get our modulus, it's 8. Then the only thing that is left of is to calculate our argument angle. Okay, so we know that we will first have to find this one, our reference angle. So we see that theta is the ref angle, and the reference angle is going to be arctan of b over a, where a is 4 root 3 and b is minus 4. But then remember, when you are calculating the reference angle, you do not have to put the negative sign in there. So you're just gonna have I don't know, 4 divided by 4 root 3. Okay, then this is basically arctan of 1 over root 3. So arctan of 1 over root 3, that is pi over 6. Okay, so this is your alpha. You know that alpha is just the reference angle. So from the reference angle, then we can find I don't know, theta. Notice that theta, this angle up to here, plus this one, they form 360, a full revolution. Okay, so that is 2 pi. So that implies now, if we take, sorry, if you want to find what is theta, theta will just be 2 pi minus our reference angle. So theta will just be 2 pi minus pi over 6. And 2 pi minus pi over 6, we get that alpha is basically going to be 11 pi over 6, right? So we get not alpha, theta here. Put theta there. This is theta, okay? Then we know that is basically our big argument of z. So our big argument of z theta is 11 pi over 6. Therefore, Z is just going to be R, it's 8, then cos of 11 pi over 6, then plus I sine of 11 pi over 6. Yeah, then we're going to have, this is our polar form for that particular complex number Z in standard form. Okay, so that is the basic idea. Say, let's do maybe one more example. Maybe we have Z equals to, I don't know, minus 1 plus I. Okay, so if we have minus 1 plus I, this one will be in which quadrant? It's going to be in the second quadrant. Okay, we have minus 1 there and positive 1 there. Say they meet somewhere here, then you can construct a straight line to that point. Then going down like that, you form your right angle triangle. Then the angle inside of there will be alpha again. So you have alpha there. Then theta is basically the angle from the positive real axis up to here. Okay, so yeah, that is the idea. And remember this. Let me put down this. The angles here is 0, here is pi over 2, here is pi, here is 3 over 2 pi. Then once you get back to that point, you have 2 pi. You have gone all around like that, 360. So that's why this one is there for 2 pi when you come back to the same point where you started. Okay, and when you go the other way around, you just make them negative. So you're going to have negative pi here. I mean negative pi over 2, then negative pi, then negative 3 over 2 pi, and negative 2 pi. Okay, or maybe let me just write them down. You start at 0, then go to minus pi over 2. This is when you're going clockwise. Okay, this is when you're going anti-clockwise, when you're going this way. These are the angles like that. Okay, but if you're going this way, the angles now it's minus pi over 2, then minus pi, minus 3 over 2 pi, then minus 2 pi when you come back there. So they are like that. Okay, so now let's come back to this one. We want R first, and R is basically gonna be root 2. So R is root 2, we get minus 1 square plus 1 square, so that will be root 2. Then now we need our reference angle first. Our ref angle will be arctan of 1 over 1. So we need just arctan of 1, so that will be pi over 4. Arctan of 1 is pi over 4. So we get our alpha as pi over 4. So this means now our theta will be what? I don't know. We are in here, the second quadrant. And we know that this whole angle that covers both theta and alpha, it's equivalent to pi. Okay. So remember this red one, it's the angle theta. So we're gonna have just pi. It's gonna be pi minus alpha to get theta. So theta will basically be pi minus pi over 4. And this is just nothing but I don't know, 3 pi over 4. So you get your argument of z, big argument of z as 3 pi over 4. So therefore it implies that z in polar form is just gonna be r is root 2 into, say, cos of 3 pi over 4, then plus I sine of 3 pi over 4. So that is the idea. That's how you do the things. Okay, if you are on the interval 0 to 2 pi. Okay, so now let's check what we're gonna have now. Say if they say we should give the polar form of z. Give the polar form of z where the big argument of z, it's now instead between pi and minus pi. Okay, it's in between minus pi and pi like that. So now we are restricted because of that reason. Let me try and plot this. So that means since we know that here we have 0, pi over 2 and pi. I'm just interested in these two angles, okay? And here we have 3 over 2 pi. Then once we come back here again, we have 2 pi. So from 0, this is where we're starting. We're starting at 0 until pi, okay? We are going clockwise. And then we're going anti-clockwise. And if we go this way from 0, then to minus pi, that means if we go the other way around, remember when we're going clockwise, the angles become negative, okay? This is the idea about the angles becoming negative. We are going clockwise, okay? So we are going from 0 to minus pi. So this is how you describe the big argument of z on this interval minus pi and pi, okay? So say we draw a straight line or a number line like that, then we have minus pi and pi here. Okay, say maybe 0 is somewhere in between them. It will be somewhere in between minus pi and pi. Okay, so the big argument of z will only lie on this region from minus pi up to pi. Anywhere else, if we extend this line here and here, it will be out of the interval, the region. It will be out of the region that we are restricted. We are restricted that we should find the big argument to be within this region. Any angle that is outside of this region, an angle that is less than minus pi and or an angle that is greater than pi, it cannot be the big argument for that type of interval. Okay, so that is the thing that you have to keep in mind if you are using the big argument of z. And also, if they do not state the fact that you should use the big argument of z between minus pi and pi, but they just tell you find the polar form of z using the principal argument. Just use the idea that it should be between minus pi and pi. Okay. So if it's stated that you should use the principal argument, just use the idea that it's between minus pi and pi and do it the following way that I'm going to show you guys now. Say for an example, you have z equals to I don't know, minus 2 minus 2i, like that. If you have something like that, then let's see, can we transform this to be in a polar form where z, our big argument of z is between minus pi and pi? Okay, we can do that. First, we can find the modulus. The modulus will just be minus 2 squared plus minus 2 squared. So this implies that our modulus basically is equals to, this is 4, then also that is 4. So 4 plus 4 is just going to be, I don't know, 8. So we're going to get our rs 2 root 2. Okay. Yeah, it's going to be something like that. That is r. Then from there, now our aim is to find theta. But then we have to first sketch this on our plane. If we put it on the real and imaginary plane, where is it gonna be? It's gonna be in the third quadrant here. This is where they are both negative. Okay, so say minus 2, it's somewhere there, and also there. So they will meet somewhere there, that point. Then you draw a straight line like that. Therefore, now what you need to do is that you construct your right angle triangle. Then you have your 90-degree here. Then here you will have your reference angle like that. Okay, so I don't know. Look, if we try and check the region, this one from 0 to pi. If we check that region, that means we are here on top from 0 to pi. Do we find our complex number there? No, z is not in either quadrant 1 or in quadrant 2 or quadrant 1. It's not in this region. That means we are down below here. We are focusing on this region, specifically on this one. Okay, and if we are focusing on that one, then now what you're going to do is the following. In the third quadrant, okay, we are in the third quadrant. You will say that you first look for your ref angle alpha, where we know it's just going to be arctan of I don't know, 2 over 2. We don't care about the negative signs. We just take the values 2 and 2. Okay, then 2 over 2 is 1. then basically here we get arctan of 1, which is pi over 4. Okay, so our reference angle alpha is pi over 4. Then now what is going to be our big argument of z? We know big argument of z is theta. So the big argument of z theta will be nothing but I don't know, the reference angle. It will be your reference angle minus pi. Okay, so this is how you find your big argument of z in the third quadrant. In the third quadrant, it will be the reference angle minus pi. Always do it like that. Okay, so basically theta is just going to be I don't know, say pi over 4 minus pi. So theta is just simply going to be nothing but what? I don't know, minus 3 over 4 pi. So this is your big argument of z. Your big argument of z is then minus 3 over 4 pi. So therefore it implies that z will be equals to, what did we get as our r? We got it as 2 root 2. So we're going to have 2 root 2 into cos of minus 3 over 4 pi plus I sine of minus 3 over 4 pi. Okay, that is how you do the things. Let's look at another example. Okay, if we look at another example, we can this time around put it, I don't know, say in quadrant 2. Let's look for something that will be in quadrant 2. So we can say z should be equals to minus root 3 plus I. So if z equals to minus root 3 plus I, then what are we going to have? We will have the following. We will have that r will be equals to square root of minus root 3 squared plus 1 squared. That will be our modulus. Then here we'll get 3 plus 1 is 4, then square root of 4 will give us 2. So we'll have r equals to 2. So we get our modulus as 2. Then now our aim is to find our angle. First, let's sketch the thing. If we sketch it, see that the real part is minus root 3, so it's somewhere there. So say minus root 3 is somewhere there. Then our imaginary part is 1. Okay, our imaginary part is 1. So they will form a point right there. Then you construct a straight line from the origin to that point. So our right angle triangle is something like that in the second quadrant. Then here we'll have our alpha. This will be our reference angle. Okay, so this time around our big argument of z lies here. So we're going to measure it from the positive real axis up to until we meet our complex number there. Okay, so this one will be theta, which we know is just big argument of z. So that is the case. Then now let's find our reference angle. That means alpha will just be arctan of b over a, and we know that b is 1, then divided by root 3. Don't take in the negative, just take root 3 like that. Okay, and we know that arctan of 1 over root 3 is pi over 6. Okay, so our reference angle is pi over 6. Now that means our big argument of z, which we know is theta, will be equals to, now in the second quad, what is it going to be? It's just going to be, I don't know, pi minus the reference angle. So this is how you do it in the second quadrant. You say that your big argument of z is in the second quad. In the second quadrant, you say your big argument of z theta is pi minus the reference angle. I mean, it makes sense because the whole angle there is pi. Then if you subtract this one, you'll just get the red one there, which is theta. Okay, so that is how you do it in the second quad. Make sure that you keep this one in mind and also that one in mind. If you're in the third quadrant, use this one. And if you're in the second quadrant, use this one. Okay, I haven't talked about the first and the fourth quadrant. We'll go to that one. I'll make an example, but clarifies for the first and the fourth quadrant. Then from there, you should be able to do the things when your big argument of z is between the interval minus pi and pi. So it will never get the hang of you. After these examples, you should get the things right away. Okay. Then now it implies that theta will be equals to pi minus pi over 6. So if theta is pi minus pi over 6, what are we going to have then? We're just going to have 5 pi over 6. That is going to be our argument angle. Therefore, z will be, what was our r? We got r as 2. So it's 2 into cos of 5 pi over 6. Then plus I sine of 5 pi over 6. Then it's something like that. Then you have transformed it into your polar form, just like that. Okay, so that is the basic idea. Now let's look at the example where we are in the first quadrant. So if we want to be in the first quadrant, we have to let them both be equals to I don't know, they should be positive, both of them. Say maybe we take 1 plus I. Z is 1 plus I. If Z equals to 1 plus I, and we try to put this on our plane, our Cartesian plane, what are we going to get? We're going to get that we have 1 there and 1 there on our imaginary and real axis. The real part is 1 and also the imaginary part is 1. So if we see that this point, okay, then after constructing that straight line, just make the dotted lines like that. Then you know your angle, it's somewhere there. Then this now, instead of being your reference angle, it will be theta, because theta is measured from here, positive, real axis, up until it meets your complex number. Okay, so that is the angle theta right away. That will not be the reference angle. It's not the same as when it's in here. Look, when it's in here, we measure theta from there and we go until we meet our complex number. Then theta is that angle here. This whole angle is theta. But then now, the one that we're going to get from constructing the right angle triangle, notice that it's not theta but the reference angle. That is the difference. Okay, but if you're in the first quadrant now, right away that will be your big argument of z. Okay, so keep that in mind. If you're in the first quadrant, that is what is going to happen. Then now let's find the modulus. The modulus will just be root 2. We just one square plus 1 square, that will be 2 under the square root. Then this is the modulus, we get it as that. Then basically now theta is just going to be arctan of 1 over 1, which is 1. So we get our angle as pi over 4. That will be theta. Theta is pi over 4. Then basically z is just going to be root 2 into cos of pi over 4 plus I sine of pi over 4. So that is the idea. We have found our big argument of z. This one is the big argument of z, like that. Okay, it's just in the first quadrant like that. And if we measure the angle from the positive real axis, then when we meet our complex number, that angle that we get, since it's inside the right angle triangle, then it is right away your big argument of z. Okay, so we can also do an example when now instead we have the thing in the fourth quadrant. Okay, so say maybe z equals to for them to be in the fourth quad, it means the real part has to be positive and the imaginary part has to be negative. Okay, I don't know, I can put in anything. Say we have 2 root 3 then minus 2i. Yeah, if we have something like that, what is it gonna be then? If we have something like that, notice that here are our modulus will be square root of 2 root 3 squared plus minus 2 squared. Okay, so r is basically going to be 2 squared, that will be 4, then 4 times root of 3 squared is 3, so 4 times 3 is 12, then plus 4, that will be 16, root of 16, then that is 4, so we get our r as 4. Okay, then now if we try and sketch or plot our complex number there, we know that it's going to be 2 root 3, say it's somewhere there, then minus 2, it's somewhere here. Then where they meet, say maybe it's here, the point, then you construct a straight line like that. Then we get our right angle triangle as something like that. So since we are looking for the big argument of z, and we know it's between pi and minus pi. Remember, we can measure it this way or that way. So it's not in there. Okay, we can only find it in this region, where specifically now it's in the fourth quadrant. So we're just gonna measure it. Is the angle that it goes from the positive real axis until it meets our complex number. So it's just going to be that angle. It's within the right angle triangle like that. So whatever angle that we get from using the right angle triangle now is just going to be our big argument of z. But keep in mind now that we are not going anti-clockwise, we are going clockwise. And when we go clockwise, the angles are negative. Okay, so that is the idea for this type of equation. So the big argument of z theta will therefore be arctan of I don't know, 2 over 2 root 3. Okay, since we are going anti-clockwise, the thing has to be negative. So if you include that negative from 2, it will give a negative angle, or you can calculate it without the negative there. Then remember that it has to be negative. Put the negative after you find the answer. So this 2 and that 2 will cancel. Basically, we're looking at arctan of 1 over root 3. And we know that 1 is just pi over 6. But then because it's the angle that we measure anti-clockwise, it has to be negative there. So the big argument of z is that. Okay, or let me just use theta in this case, because already I stated that is theta. Then that is the solution of the angle. Then we get z now to be 4 into cos of minus pi over 6. Then I don't know, plus I sine of minus pi over 6. Then that is the solution. So I think this has to be sufficient for you guys to understand the idea of big argument being between 0 and 2 pi, and when big argument is between minus pi and pi. Okay, then yeah, this is sufficient to get you guys through tomorrow's test. I hope you guys will look through the video and understand everything.